I'm going to assume that we don't need to wait for the recording to introduce the speaker. So hello everyone, it's my pleasure to introduce Laszlo Erdös, who will be giving a talk today. And I suppose I'll just tell you briefly a few things about him. So Laszlo received his PhD in 1994 from Princeton University and his habilitation from the University of Vienna in 2001. He's received numerous awards and published many papers, including, just to name a few, he was recently named a Fellow of the American Mathematical Society, and he's been elected as a corresponding and foreign member of the Austrian and Hungarian Academy of Sciences, respectively. And since, he recently received an ERC advanced grant, and he has been a professor at the Austrian Institute of Science and Technology since 2013. And it's a slightly funny story about that. The first time I saw Laszlo give a talk was at the Park City Mathematics Institute special program on random matrix theory. And he opened his talk by giving an advertisement about how great the IST was as an institution to work at. And in order to really make sure that he was encouraging everyone to consider the institution, he put up a slide with a picture of all the different coffee selections available from the nearby Café Mozart. And I tried yesterday to determine if the cafe still existed, but I wasn't able to tell. But his record leaves no doubt that Laszlo still exists. And I would like to introduce him now to give his talk on universality phenomena for random matrices.
Okay, thanks very much. Thanks so much. Can you hear me? Okay, very good. Okay, so thanks very much for the organizers for inviting me to this conference. I'm coming from a little bit different community. I'm from random matrices, more from probability, not so much from operator theory side. So the community is a little bit different. I will give you a little bit overview talk about what we are interested in random matrices. And of course it has some operator theoretical aspects as well, but it will be slow and there will be lots of pictures, there will be no proofs, it's only some main theorems and main phenomena. So let me just start to show my collaborators. I will talk about several results over a long multi-year project. Some of them are actually here, some of them will give talks in the random matrix section. So Vova, Oleksiy, and Hongchang are here. They will give you more details in the appropriate sessions. Now this is this IST. This is the place where I'm from currently. IST stands for Institute of Science and Technology in Austria. This is located near Vienna, around 15 kilometers away. And it's a reasonably new research institute. It was founded around 15 years ago. It's only we don't have undergraduate students, it's only a research institute and postgraduate or graduate studies institute. And most importantly, I would like to point out that we do have all kinds of openings, both on graduate student level and also on faculty position level, postdoc level, and so on. So if you are interested in coming to a great place, this is really a great place to be, then check out our webpage, and there are possibilities, opportunities on all levels. I didn't put now the coffee machine on, but be assured that the coffee machine still exists, and also the excellent coffee in Vienna still exists. Okay, so this was the advertisement, so let me come to the actual part of the talk. So the whole random matrix story starts from Eugene Wigner, but I usually like to put this on the first page in the form that this is the question which the mathematicians fail to ask. Sometimes it happens, maybe not so rarely, that we need a physicist. We as mathematicians, we need a physicist to point out the right question, and in that case it was Eugene Wigner. Namely, he asked this very natural question: what can be said about the eigenvalues, the statistical properties of the eigenvalues of a large random matrix? So this is a question which he asked around the 50s, and in retrospect, this is surprising that mathematicians have not thought about this question before, because the ingredients, eigenvalues, random matrices, randomness, and so on, they have been around for many, many decades in the 50s, but still we need a physicist and a physics insight to ask this very exciting question. And especially the reason why Wigner was interested in it, that he was looking for some universal pattern emerging in the statistics of the eigenvalues. So the situation is the following. We look at a large matrix, n by n, and capital N will denote the size of the matrix. Typically n is large in the mathematical theorems, n will go to infinity. So we look at a large random matrix. The easiest way to think about it is that you put in every matrix element, you flip a coin, and then you put an IID, independent, identical, distributed random variable in the matrix element. Except that Eugene Wigner, as a physicist, he was interested in quantum mechanical Hamiltonian. So this matrix, this random matrix, is supposed to model a quantum mechanical Hamiltonian, which means that it has to be Hermitian. So he looked at random Hermitian matrices, which in his case meant that all entries on the upper diagonal, above the diagonal, they were independent, and then below the diagonal, it's whatever the Hermitian conjugate dictates. And then the question is that you look at the eigenvalues. So there is, of course, a functional relation how you compute from the random matrix elements of the n eigenvalues. This is a complicated procedure, complicated functionality. And then you look at the question what kind of statistics emerges on the level of the eigenvalues. What is the statistics, what is the distribution of the eigenvalues. And notice this is a highly non-trivial question, even though you put some fairly trivial statistics on the matrix elements, just for example independent, choosing the matrix elements independent. Of course the eigenvalues themselves will be a complicated function of these random variables, of these n squared random variables, so themselves will typically be not independent, they will exhibit a complicated statistics. Okay, so this is what Wigner asked this question, and the vision what he had is that he thought that this is the last line here, that these energy levels are the physics terms for eigenvalues, that these eigenvalues exhibit some universal pattern on the level of the statistics. So it means that you should think of them as not deterministic object but as random variables, and then their distribution should be universal. If you ask the right question, then the corresponding distribution should be universal. Universality here means that the answer, the distribution, does not depend on the details of the input distribution. So for example, for a standard random matrix, you can choose these matrix elements according to basically any independent distribution. You can flip a coin, you can take a Bernoulli, you can take Gaussian, you can take any other distribution for the matrix elements. No matter what you do, the statistics of the eigenvalues, it's not the individual eigenvalues, but the statistics will be independent of the choice of the initial distribution. I will explain it a bit more detailed. But the reason why Wigner was interested in it, because he looked at the actual measured data of heavy nuclei, so eigenvalues or energy levels of heavy nuclei, which are supposed to be the eigenvalues of some big Hamiltonian, and he found that these eigenvalues, especially the gap distribution of the eigenvalues, which means that the distance between neighboring eigenvalues, exhibits some very typical, very universal pattern. So that's how the whole idea came from. Now let me go back. So this was the physics motivation. Let me come back to the probability theory motivations. I will list 3 basic theorems about probability theory. These are toy models. These will exhibit these will sort of represent the type of theorems which we will prove about random matrices. So this is not about matrices yet. This is probability 101. So take a sequence of IID, independent, identical, distributed random variables, fix the expectation, their variance, and then the first thing what you learn in probability theory, in any serious probability theory course, is the law of large numbers, which in physics terms means self-averaging. For mathematicians use the word law of large numbers, which means the following, that you take these IID random variables, you add them up, you add up the outcome of the coin flipping, you normalize by n, and the whole thing converges to its expectation. This is a very well-known theorem. And this holds in very strong sense, especially it holds in almost sure sense. The next level, which you learn in probability theory, is the central limit theorem, which asks about the fluctuations around the law of large numbers. So the law of large numbers is a deterministic limit. Okay, so you subtract from this normalized sum from what it should be, what the limit should be. This object is still a random variable, but it's a random variable which goes to 0 unless you normalize it differently. So it turns out that if you multiply the whole thing by square root of n, then you magnify the fluctuation to something which is visible, and the appropriate normalization tells you that the distribution tends to the normal Gaussian. So that's the central limit theorem. And if you wish that this is the first and most prominent example of the phenomenon of universality in natural sciences, if you wish, because no matter what the initial distribution of the axes were, the outcome of their fluctuation, of their cumulative fluctuation, is always the normal distribution. So you can have coin flip, you can have uniform distribution, Gaussian, no matter what you put on the left-hand side, the limit where it converges to is always Gaussian. This is one thing which you should notice. The other thing is that there is a big difference between these two types of theorems. The first one is in almost surely, so the right-hand side is a deterministic object. This is just a number, the expectation. Here the distribution is in terms of probability, the limit is in terms of distribution, which means that the limit itself is a random variable, and there's a proper way of defining this limit when you test it against continuous functions. Now, so these two things which you learn in probability 101, and depending on your probability course, you may learn the third one, but maybe it's probability 102. This is called the extremal statistics, which is a similar question, but there you ask, so you have a sequence of random variables, but then you ask what is their maximum, how does their maximum behave? So take their maximum. Okay, this is typically a fairly big object. If you have random variables, then the maximum may be even bigger than the typical size. So again, you have to normalize it. First you subtract something and sequence an, I will come back to that, and then you may have to magnify the whole thing with another scaling factor. And then under certain fairly general conditions, it's still true that this appropriately scaled random variable converges to a universal distribution, which in that case is called a Gumbel random variable. It may not be so well known, but here is its distribution function. It's a double exponential distribution function. This is also a very universal object, similar as the normal variable. Now, of course, what the an and bn are, these depend on the distribution of the original axis, but the important thing is that after you rescale it properly, the limiting distribution, the distribution of the natural fluctuation is universal, namely in that case is the Gumbel. And just for an example to indicate what these an and bn's are, if you started with normal random variables, then you can compute the an is a fairly complicated object. It's actually a three-term object. There's a square root of log n term, there's a log n divided by square root of log n, plus a constant per log n term. So this is the typical size of the maximum, and then a square root of log n factor, which you have to multiply it to get a non-trivially fluctuating object. So the pattern is the same as in the central limit theorem. You have to subtract something and you have to multiply it by something, but these two somethings are more complicated. Okay, so now we will look at, so these are the three types of questions: law of large numbers, central limit theorem, and extremal statistics, and we will look at similar questions now in case of random matrices. So let me just give you the definition of the Wigner matrix. I already told you that in words, but here is the precise definition. Take an n by n Hermitian random matrix, which means that the entries are IID, independent, identically distributed, up to the Hermitian symmetry. And then we take a normalization just for convenience, that we assume that the expectation is 0 and the variance is 1 over n. That turns out to be a convenient normalization for this random variable, but apart from that, the distribution can be basically arbitrary. And then the first major theorem in the field is the famous Wigner semicircle law, which says that the empirical density of the eigenvalues, in physics terms this is called the density of states, converges to a universal, to a very well-defined distribution, which is the semicircular law. It's exactly because it's given by a half circle. And again, it's irrespective of the distribution of the matrix elements. So you should think, I didn't write up the precise formula what the limit means, but what you see here is the eigenvalues, an empirical, one choice of an empirical eigenvalues, and then this density of eigenvalues is still it generates a random measure, but then it converges to a deterministic measure, and this deterministic measure is exactly the semicircle law. Now, you should also notice that in this, so this -2, this fixed deterministic semicircle law is due to the normalization. Of course, if I change the normalization, then the whole thing gets rescaled a little bit. The important thing also that if you look at individual eigenvalues, then the eigenvalues, there are n eigenvalues here, so the typical distance between neighboring eigenvalues is 1/n, roughly speaking. But the Wigner semicircle doesn't really tell you anything about individual eigenvalues. It's a theorem about the empirical density, which is a global question. So you ask, for example, you take a test function on the larger scale, and you evaluate this test function against the eigenvalue, individual eigenvalues, and then this evaluation converges to the integral of the test function of the semicircle law. Such a question, such an observable, does not depend on individual eigenvalues. It's too crude type of question. But the important thing is this is a law of large number type of results. So you have a random object, the random density of states of the eigenvalues, and the limit is a deterministic object, the semicircle law. Now, the Wigner semicircle is the first theorem, but that's not the most important theorem or not most important phenomenon in the business. Wigner's revolutionary observation was that if you look at the gap statistics, eigenvalue gap statistics, then this quantity, this statistics is even much more robust. It depends only, it doesn't depend on any details of the ensemble, it depends only on one thing, whether you take what is the symmetry class of the matrix. I didn't mention that before, but if you want to create a random matrix, a Hermitian random matrix, then you may distinguish between Hermitian or symmetric matrices, namely you may distinguish whether the matrix elements are complex numbers, and you take a Hermitian matrix, or the matrix elements are real numbers. And this is the only thing which matters in the Wigner gap statistics, whether you take real or complex matrices. Now, what is this gap statistics? So the gap statistics is exactly what the name says. Here it is. You take the eigenvalues lambda 1, lambda 2, and so on, ordered increasing way, and then you take the I plus 1 minus the ith eigenvalue. So you take here some two neighboring eigenvalues. The distance between two neighboring eigenvalues is, of course, 1/n. So in order to see a non-trivial distribution, you have to rescale it by a factor of n times the local density, and this is the quantity. This is a rescaled gap, whose distribution turns out to be universal, and the curve looks like that, roughly speaking. And this is what you see here is a histogram of some large number, some large matrix. But the most important thing at this curve, the shape of this gap distribution, is the density function of this random variable. This shape is completely universal. It's independent of many things. It's basically independent of everything. It's independent, for example, on which eigenvalue you look at. You can look at eigenvalues here. You can look at eigenvalues here. Doesn't matter. But more importantly, it's also independent of the original distribution. There's a matrix. The matrix elements have a distribution. This gap statistics, this curve, is universal. It doesn't feel that. It doesn't feel what distribution you fed in. The only thing that it feels is that whether you fed in real random variables in the matrix element, real matrix, or complex, genuinely complex matrix. Now, this universality formula was formulated as a Wigner-Dyson meta-conjecture in the 60s, and it took around 50 years until it was eventually proven in full generality. I mentioned, I showed the results inside the spectrum. There is a little bit different story around the edge. You can imagine that around the edge, the spectral edge, the density goes to 0. So the distance between neighboring eigenvalues is not 1/n anymore. It's actually 1 to the minus 2/3. And it turns out that there is also universal statistics at that level, at the edges. The statistics is given by a different curve. It's not the Wigner-Dyson distribution, but it's a famous Tracy-Widom distribution. whose universality was actually proven earlier. For some reason, the edge universality is an easier question. Okay, so now you should notice that both of these distributions, the Tracy-Widom, which I didn't show the picture, but it's there, and the gap distribution, the Wigner-Dyson story, these distributions are completely new. They are not the central limit theorem, they are not the Gumbel, they are not normal, and so on. They were not known before. And more importantly, there is a point process behind that. So here I'm just looking at a very particular statistics of these random points. I just look at the gap statistics, difference of neighboring eigenvalues. But I can look at many other questions. For example, I look at the joint k-point correlation functions, joint marginal of the joint distribution of the few neighboring eigenvalues, not just the difference of the two. I can look at it as a point process. And then I can ask, what is the distribution of this point process? And it turns out that this is also a very novel thing. Most importantly, this point process is strongly correlated. So the eigenvalues feel very strongly each other. And this is clear from the gap distribution, especially in this regime. You see that the density of the gap distribution goes down to 0 at around 0. This means that the probability of neighboring eigenvalues being too close to each other is suppressed. That's called a level repulsion. So in particular, it means that these eigenvalues repel each other. This is a basic phenomenon which actually Wigner observed in quantum mechanics. From measured data of energy levels, and more importantly, what's behind that is that these point processes, what emerge from the eigenvalues, these have a so-called determinantal structure, which I will not write up here, but those who went to Tom Clay's talk yesterday got a huge detailed introduction about determinantal processes. Most importantly, that these determinantal processes are very different from the standard point processes which you may learn in probability 101 or 102, namely the Poisson process. The Poisson process is the process of the completely independently thrown points on a real line. These eigenvalues are not like that. These eigenvalues are strongly correlated. They have a very different structure. And that they are being determinantal means that their correlation functions are given by determinants, which means that you can do lots of very beautiful calculations with them. Okay. Now, so this story was about the so-called Wigner matrices, which meant that the matrix elements are independent, identically distributed. Now, in the last decade, both of these universalities, the Wigner-Dyson meta and the Tracy-Widom universalities, have been greatly extended well beyond the Wigner matrices, especially approaching towards more realistic physical systems, because there is an even bigger universality conjecture behind all this Wigner model, which I will come to that. But just in a nutshell, it says that it's not just the IID random variables in the matrix element is not important. That's the spectral statistics, especially the gap statistics, should be universal under even much more general situation. And the research in the last decade aimed at to sort of extend our horizon, test the boundaries of this even bigger universality conjecture, how much I can generalize the Wigner matrix in order to still get universality. So there will be a few possible extensions. One of them is the so-called deformed matrices, which means that you can add a non-trivial deterministic matrix to your random matrix. You can also take some structured matrices. So far, our matrix, the Wigner matrix, was IID, which meant that its physics terms is a completely mean field model. There is no difference between H12 and H23, for example. But then you can imagine some structured matrices. For example, you can have some block matrices where the blocks have different variances. You can have even more general variable variance matrices when the variance of the matrix elements is not 1 over n at every entry, but something which depends on the location of the entry and so on. You can have band matrices, which means that which is not a fully filled matrix, but a matrix where the elements around the diagonal, in the diagonal, and next to the diagonal regions are filled, but apart from that it's zero. So there are lots of possibilities. You can imagine that There are many possible random matrices, structured matrices in the universe. You can also put in correlated entries. An important property of the Wigner matrix was that the entries were independent, but it's not necessary. You can also put in some correlations. You can also do sparse matrices. It's a very popular topic especially in combinatorics, because a sparse matrix is typically can be viewed as a 0-1 sparse matrix, can be viewed as an adjacency matrix of a large graph, and then it's understandably it's an important topic. You can also take some heavy tail distribution and so on. I mentioned two universality classes, the Wigner-Dyson, which was valid in the bulk of the spectrum, and the Tracy-Widom, which was valid in the edge of the spectrum. It turned out that there is a third universality class, which is called the Pearcey universality class, which appears at the cusp, if the density of states have a cusp singularity, then a third universality class appears. Now, this is the most important general belief in the whole subject. This is a very bold physics conjecture, which of course mathematicians are very far from proving, but it serves as a motivation, inspiration, what we would like to do. So the general belief is that the universality of the local eigenvalue statistics should hold for any sufficiently random matrix. A matrix here means a Hermitian operator, in the delocalization regime, in the sense of the Anderson metal insulator transition. I don't expect that you know what Anderson metal insulator transition is, but the delocalization regime I can roughly explain. So delocalization regime means energy level energies where the corresponding eigenfunction, eigenvector, is more or less uniformly distributed in the whole space. Every matrix element is more or less, roughly speaking, equally occupied. The physics behind that is going back to random Schrödinger operators, which I will not explain it here, but there's a very natural and very compelling physics motivation behind this business. Okay, so now let me come to explain what is the basic equation which governs the density of states once you go beyond the Wigner situation. So Wigner situation, IID centered entries resulted in the semicircle that you can do by fairly elementary methods. If you take a more general random matrix, a Hermitian matrix, it can have even correlated entries. Then this matrix can be characterized by a data pair. One of them is a matrix, it's a deterministic matrix, which you can think of the expectation matrix of the H. The Wigner matrix has zero expectation, but you can generalize it to an arbitrary expectation. This is one ingredient, and the other ingredient is a so-called correlation operator, correlation tensor, which basically encodes all the correlations, the 2 point functions, 2 point distributions of all matrix elements. In the simplest way, you can express it in such a way: this is an operator, it's a super operator acting on matrices in the following ways. They take the expectation of HR. HR is the variable. So this one includes all the correlations of the matrix elements. Now, you can ask the question, what is the analog of the semicircle? So there should be a law of large number. If you take a random matrix with this expectation, with this covariance, hopefully the distribution of the eigenvalues will converge to something. It's not the semicircle, but something else. And what is this object? How to compute it? And here is the way to compute it. So you have to first solve something which is called the matrix-Dyson equation. It's actually also appeared in mathematics before, but I mean Dyson is a good name. So the matrix-Dyson equation is the following. It's a nonlinear matrix-valued equation. The M is the unknown, MZ is the unknown matrix. Z is a spectral parameter. You have to compute it for every element in every value Z on the upper half plane. And it looks like that the inverse of M equals Z minus this A plus the S, this S operator acting on M itself. So this is like if you wish, like a quadratic matrix equation, 1 over M equals to something which is linear in M. Now this equation has many, many solutions, but we are interested in the solution whose imaginary part is positive in the matrix sense. And it turns out that under this restriction, this equation has a unique solution. And then once you have this M, then you have to compute this imaginary part and this boundary value of this imaginary part. Imaginary part, then you have to take the trace, the normalized trace of that to get a number, and you compute the boundary value as you go down from above in the complex plane to a real value x. So you compute the boundary value of this M, and that will be the density of states. That function, that rho, is a density, and this will play the role of the semicircle. This replaces the semicircle in general. Now, we had an older theorem with several people, which says the following, that under some mild condition, namely under the condition that this super operator, this covariance operator is bounded from below and from above by the trace, which is a sort of mean field condition, under this condition, this density of states behaves very nicely. In most cases, of course, you cannot compute it explicitly, but basically you know everything about it, what you want to know. So its support consists of finitely many intervals. The semicircle has only one interval, but it can have several of them. The rho is real. This function rho, the density function, is real analytic, away from the edge, away from the points when it goes down to zero at the edges of the support. And then at the edges, or when the rho becomes zero, it can have two types of singularities. Either it has a square root singularity like the semicircle rho, or there's a third possibility that it can happen that the two edges, when the two intervals of the support sort of touch each other, then you see a degenerate square root singularity, and then it degenerates into a cubic cusp singularity when these two intervals touch. But then, so there are these two possible singularities, and nothing else can happen. So this is a very general fact that there are no other types of singularities. And so once you have that, then you can ask the local statistics in each kind of singularities. Now there are important special cases which I already mentioned before. So the deformed Wigner case is one of them, when you still assume IID, but you drop the centered condition. So basically the S is still trivial, but A is not trivial. Or you can take the so-called Wigner type matrices when you keep the independence but drop the identical distribution. In that case, it's still the equation, the corresponding matrix-Dyson equation becomes somewhat simpler. So there are special cases, and especially Alexis and Wawastok will address this, what we know about them, what we know about the special cases on Thursday. Okay, so far I talked about eigenvalues. Now, you may ask what happens about eigenvectors. That's another natural question, natural object. And the answer is the following. First of all, much less is known about eigenvectors. But the first answer is the following, that U1, U2, and so on is an orthonormal eigenbasis of H. I mean, typically there is no degeneracy, so we can assume that each eigenvalue is simple. Now, what you expect very naturally, if the H is like a Wigner matrix, a very mean field random matrix, you expect that the eigenvectors are also very random. They are as random as possible. What does that mean? And there you have n eigenvectors. These form an orthonormal frame. So the most natural thing is, the most random thing is if they were hard distributed on the n ball. And that's exactly what happens if you, I think it's the next level, so this fact that the eigenvectors are hard distributed, this is a triviality if the original matrix has Gaussian entries. I didn't say it before, but there's a very special ensemble among the Wigner ensembles. This is the Gaussian unitary or Gaussian orthogonal ensemble, abbreviated by GOE or GUE, which just stands for the fact that if you choose the matrix elements to be Gaussian, and then it turns out that if you have Gaussian entries, then there's a huge invariance going on, a unitary invariance, simply because if you conjugate a Gaussian random matrix by unitary matrices, then you still get, then the outcome is also a Gaussian matrix. So the distribution remains invariant under unitary conjugation. which fact easily seen to imply that the corresponding eigenvectors in that case are invariant under the usual group on the Sn, the usual UN or On group, which means that then the eigenvectors must be hard distributed. So this is the trivial case, but this is true only because the entries are Gaussian. And then according to the universality principle, you expect that this fact, or at least in some asymptotic sense, this fact does not depend on the original Gaussianity of the entries. So for example, naturally you can ask the question, take a Wigner matrix, say II the entries but no Gaussian. Is this true that the eigenvectors still form an asymptotically hard distributed n-tuple? And this is actually true in some sense. Let me list a few results what we know about it. But these theorems are very highly non-trivial. So for example, what one can prove is that you take the ith eigenvalue and eigenvector j's, i's or j's, and then you take a matrix element of that. It actually doesn't have to be the same I. So you take the ith eigenvectors, but the AI doesn't quite make sense. So you take the ith eigenvector and the jth matrix element. This AI is a typo, and then you have to scale it up to be an order 1 object because this is a normalized eigenvector. So each matrix, each vector, each element of the eigenvector is of order 1 over square root of n. So if you multiply it back, scale it back, then these are jointly Gaussian elements. These form a jointly Gaussian, finitely many of them form a jointly Gaussian bunch of random variables. Here's one level, one indication that it's in some sense asymptotically hard. A more important, a more general manifestation of this universality is what is called the eigenstate thermalization hypothesis in physics, and it's also known as the quantum unique ergodicity in mathematics. These are the same things depending on whether you come from physics or mathematics community. And this says the following: take a deterministic matrix A, it's very important as deterministic, and then you take the matrix element, you sandwich this A between two eigenvectors. So Ui and Uj, these are the random eigenvectors, but A is deterministic. In physics, that's a very important quantity. It's also mathematics, but in physics, these are measurable quantities. You think of it as Ui are the eigenvectors of some quantum system, and A is an observable. And this is the measure, if I equal J, then this is a measured value. You expect the value what the quantum measurement is supposed to provide you. So now this is a random variable, and what is this? And it turns out that if I equal J, then it's very different than if I not equal J. So there's a leading term, which is a deterministic term, according to the law of large number, which is that delta Ij times the average trace of the observable. So that's the law of large number level of the limit. And then plus there is a fluctuation. The fluctuation is of order square root of n. And then the fluctuating Rij is a random variable, which turns out to be normal. So the fluctuation is normal here, and the variance can be computed. The variance especially depends on the traceless part of A. So A is a general matrix. If you subtract from that the average trace, then you get a traceless matrix. I denoted by this A circle. And what matters is, what determines the fluctuation is the traceless part, the Hilbert-Schmidt norm of the traceless part of A. I mean, it's understandable. Just think about if A is only diagonal, if A is only a constant matrix, an identity matrix, or A circle is 0, then of course there is no fluctuation. The Ui, Uj is delta Ij deterministically. But once you have a traceless part, then you start having a fluctuation. Okay, so I mean this has especially if you think about quantum unique ergodicity, this type of questions have a long history. It's actually a random matrix version of the Framer-Schnirelmann theorem. Let me not go in quantum unique ergodicity. Let me not go into that. On the physics side, there has been many predictions about it, Deutsch, Feingold, Perez, these are physics papers, and then more recently there have been many mathematical papers which prove this ETH, eigenstate thermalization hypothesis, again in increasing generality. I just presented the Wigner case, but you can ask the same question for more general random matrices. The spirit of the result is the same, of course, the expectation, the limit, and also the limit of the limiting variance, they change, they depend on the actual ensemble. You can also ask a similar you can also ask a similar question about the extremal statistics. Remember, I started with law of large numbers, central limit theorem, extremal statistics. If you wish, then this part is the law of large number, this part is the central limit theorem, and this last thing is the extremal statistics, where I ask the question, here I just ask the question for diagonal elements, so UI, A, UI, take the sandwiching of A between an eigenvector, but I take the maximum of that, so I take all possible, take this observable value of this observable all possible eigenvectors. Again, you have to do appropriate rescaling, but the answer is that it becomes a Gumbel distribution. So remember, Gumbel was this universal distribution for the extreme or the maximum of independent random variables. This UI, AUI, of course, for different i's are not independent. They come from the different eigenvectors of the same random matrix, so there's a non-trivial correlation between them. But nevertheless, in certain regimes, we managed to prove that this is still Gumbel distribution. Okay, so let me just give you a state of the art of various results. I mean, I just flashed up a few possible results, but there's a bigger picture behind that. So first of all, so far I talked about the Hermitian case, and in the second part of the talk, in the last 20 minutes, I will talk about non-Hermitian situations. Let me just wrap up the Hermitian situation. So for example, I mean the Gaussian GUE, GO are the most basic examples. Then you take Wigner matrices, but then you can go beyond that and you can take more general matrices. And then the most important, the three most important thing is that there is a density of states which is given by the semicircle law, case of Wigner, given by the solution of this matrix Dyson equation, case of more general random matrix ensemble. Then you have the Wigner-Dyson bulk statistics, and you have the Tracy-Widom edge statistics. These are the universal statistics about eigenvalues. It's also known, and then we know the asymptotic Haar universality, which is also the quantum unique ergodicity for the eigenvectors. Now, this was the Hermitian world. Now I ask myself, what happens in a non-Hermitian situation? So the only difference in the non-Hermitian situation is that I drop this condition. Drop the condition that HAB is the HBA conjugate. And the simplest case in the simplest matrix ensemble is the Ginebra ensemble. It's called the Ginebra matrix ensemble, which means that, which is sort of a counterpart of the GUE, the matrix, the n by n matrix elements are independent Gaussian, and every matrix element is independent, so there is no Hermitian symmetry. Or you can take more generally the IID random matrix. This is the analog of the Wigner, and for some reason the IID random matrices do not have a particular name. We just call them IID. So this is a situation, the matrix elements are IID independent, identically distributed without any symmetry. In that case, of course, the spectrum is not real anymore. This is a genuinely non-Hermitian matrix, so the spectrum is complex. And it turns out that the density of states is given by the so-called circular law. I will show a picture later on. The circular law means that the eigenvalues are distributed uniformly on the unit disk. So this is the law of large number level, the semicircle. Then there is a universality of the bulk and the edge eigenvalue statistics. This is also known, especially the bulk statistics. The universality of the bulk statistics was a long-standing open question until last October, where two outstanding young researchers, RANMAT and Mohamed Osman, proved it. And then, so this is already known. The last question, the last story about the eigenvectors, this is still largely open. In the non-Hermitian case, there are conjectures, but we don't know how to approach that. And And this is still the IID. Now you can go beyond the IID in some situations, so especially in the Hermitian case, you can do further generalizations, but in the non-Hermitian case, much less is known. Now, there's a general pattern behind that, and also this general pattern guides our proofs. The pattern is the following: that typically the Gaussian case, which is either the GUE, GO in the Hermitian world or the Gini-Brech case in the non-Hermitian world, typically the Gaussian cases are explicitly computable. These are not, computable, but so for example, if you want to know the gap distribution in case of the Hermitian situation, and this distribution can be computed more or less explicitly. It doesn't necessarily mean that you can get an explicit formula, but you have procedure to do calculations very precisely. So in this business, usually the Gaussian models are well understood. And then you need sophisticated techniques to show that the answer does not depend if you change the distribution from Gaussian to something else. Now, at first sight, this may look like some perturbation theory. You start with a matrix, every matrix element is Gaussian distributed, and instead of Gaussian, you change it to something else. But it's very well beyond the perturbation theory. Just think in such a way that the eigenvalues in my scaling live on a scale 1 over n. The distance between neighboring eigenvalues is 1 over n, so if you make some error in the perturbation theory of order 1 over n, then in principle you can already screw up the answer. On the other hand, if you already change one matrix element in the big matrix, an fixed H, A, B, and the size of the H, A, B is of order 1 over square root of n, its variance is of order n. So just by changing one matrix element already introduces an error of order, naively, by naive perturbation theory, already introduces an order 1 over square root of n. And then when I compare a Gaussian matrix with an IID matrix, then I'm changing the distribution, not just one, but all the n squared matrix elements. So just try to indicate that this is very well beyond any kind of perturbation theory. You need something much, much more sophisticated than just naively perturb the IID matrix to a Gaussian. Okay, so now let me explain a few things about the basic tools, basic scales and the tools. So when I talk about scales, I mean in the eigenvalues in the spectrum. So what I drew you the Wigner semicircle, that was a macroscopic scale. There you see all the eigenvalues in your window. You can ask a more refined question, which I call the mesoscopic scale, which is on a smaller scale, on a scale when you don't see all eigenvalues, but you still see more than order 1 eigenvalue, somewhere in between the very fine microscopic scale where you see individual eigenvalues and the scale where you see all eigenvalues. And the way to approach to this scale problem is the resolvent. I mean, the resolvent is convenient for many, many reasons. And the main phenomenon here is that the resolvent H random matrix Z is a spectral parameter in the upper half plane. That the resolvent typically becomes deterministic. There's a law of large number for the resolvents, even if H is random, as long as the imaginary part of the spectral parameter is a little bit bigger than 1 over n. And this is understandable because when you look at the resolvent with a spectral parameter, with a small imaginary part, and typically the imaginary part tells you the scale of the resolution of the spectrum on which the resolvent understands, on which scale the resolvent catches the spectrum. So if the eigenvalue spacing is 1 over n, so if your imaginary part is bigger than 1 over n, then you see you have a quantity which feels the effect of not individual eigenvalues, but feels the effect of many, but not too many eigenvalues, depending how much bigger IMZ is versus 1 over n. So this phenomena that the resolvent becomes deterministic, this has been used for many technical parts of the proof. So this a priori bound for the real Park universality proof. It also can be used directly for the edge universalities. In some sense, the edge is easier. Now you can do directly with resolvent methods. And then also you can use it in what is called the Green's function comparison theorem. I just formatted it here very roughly. Basically says the following, that if you have two matrix ensembles in such a way that the matrix element, the distribution of the corresponding matrix elements match up to 4 moments, then so they don't have to be the same in distribution, but the first 4 moments have to match, then the corresponding local eigenvalue statistics is the same. So this was about mesoscopic scale, and then if you want to know you want to know universality questions about individual eigenvalues, then you have to go to microscopic scale, so a scale which is not really accessible by resolvents, which means that the imaginary part has to be smaller than 1/n, then the resolvent becomes crazy, becomes very much oscillatory, very much fluctuating, so then you need new methods. And basically I just listed three possible methods. I will not talk about them. Each of them would take a separate lecture. One method is the famous Dyson-Brownian motion, which is a very special stochastic differential equation for the eigenvalues, and later on it was also done for eigenvectors. So this is currently this is probably the most powerful method to prove universality on all kinds of levels, eigenvectors or eigenvalues. There's another very compelling idea, the supersymmetric formalism, which is a very fundamental physics idea. Unfortunately, it's very hard to make it rigorous, as very often happens with physics arguments. It's obviously there is a truth behind it. It's a calculational tool for physicists. It always gives the right result, but mathematicians don't exactly know why. Very few people work with that, and from a rigorous point of view, especially Maria and Tatiana Sherbina. In some cases you can do rigorous proofs, but it's obvious that the method should be valid for much more generality than what we can do mathematically. And then there's a third method, which is called the partial Schur decomposition. This is a quite explicit Gaussian calculation, but a very smart one. So especially these recent results of Maltzam, Osman, and Osman, which proved the bulk universality for the non-Hermitian case, relied on that method. Now let me come in the last part. Let me come to some new results about non-Hermitian universality, which was actually advertised in my talk. This is sort of the latest result what we have here. So let me just mention that non-Hermitian matrices are much less studied than Hermitian matrices, although similar universal phenomenon should hold. And technically, of course, it's much harder. Everybody knows that any kind of perturbation in non-Hermitian matrices, eigenvalue perturbation is hard. So this is one typical motivation for studying the question what I'm doing now. This goes back to a famous paper of Robert May, who was a biologist, and he looked at the following question. It's a very innocently looking system of a linear ODE system, so U is just a vector, time-dependent vector, Cn, and then you take as you learn in ODE 101, the first order differential equation with a coefficient matrix X. X is a big matrix, which is supposed to be a random matrix. So just take IID matrix segment as we discussed here. This -1 is just a balancing, minus identity is a balancing, not important, and G is a coupling constant. And the question what Robert May asked is that how to tune this G here. Suppose that X is a random matrix. How to tune this G here so that the U is neither blowing up nor goes to 0. I mean, everybody knows that the solution of an ODE, system of ODE like that, it's typically given by the matrix exponential, which depends on whose size depends on the largest real part of the largest eigenvalue. So it has a tendency either to blow up to infinity exponential or to decay exponentially fast to 0. And if the vector of U represents some kind of biological agents, for example, some population or some neuron networks or things like that, there are many examples, then typically in reality you have the equilibrium. So you have neither exponential decay nor exponential blow up. Both of them are some kind of catastrophic situation. So you are asking the very fine tuning of this G, of this coupling constant, which avoids both of them. In order to do that, you have to know very precisely the maximal of the real part of the spectrum of this random matrix. And this is what we do here. So here's just the introduction, a precise definition of this IID random matrix. I already defined it or told it to you before. So you take a random you take an IID copy, you take a random variable chi, expectation 0, variance 1, and then you take a rescaled copy, 1 over square root of n rescaled copy of this single IID, of this single random variable, independent copy for each of the matrix elements. And the 1 over square root of n is the right normalization. Here, believe me that if you do a little calculation, you can convince yourself that the typical eigenvalue, the size of the typical eigenvalue is of order 1 under this normalization. And the picture is like that. This is how the numerics, what the numerics gives to you. These are the eigenvalues for 50 by 50 matrix. This is the same for the complex entries. The two pictures have a little difference. So this is a real case, this is a complex case. In the real case, of course, you know the spectrum is symmetric to the real axis, and you can see that. In the complex case, there is no such symmetry. Also, in the real case, there are real eigenvalues. In the complex case, generally, there are no real eigenvalues. But otherwise, the two pictures are similar. And if you increase the n, then you see very nicely what I called the circular law, which is the density of states or limiting density of states of these eigenvalues, converging to the uniform distribution of the disk. I didn't write it up as a formal thing, but everybody can imagine how it looks like. Okay, so now, so this is about the macroscopic scale. Now you can ask the local statistics, which is the microscopic scale, and you can ask two different questions. You can ask the bulk statistics when you take something within away from the edge, and you magnify it in such a way that you can see individual points. The typical distance between neighboring eigenvalues is 1 over square root of n. So you have to magnify it by a factor of square root of n so that you see a point process which has a chance to converge to something, and indeed it converges to something. It's a determinantal process again, which is universal. And the same thing happens at the edge, but of course the process is different because the fact that there is an edge, it should show up in the limiting distribution. So the edge was proven by us a few years ago, and the bulk was proven very recently. Okay, and now let me come to the last thing. This is extremal statistics about the maximal real part of the rightmost element of the spectrum. Or you can also ask this a different question. You can ask the similar question with the spectral radius. What is the maximal of the absolute value, the largest eigenvalue? So here are the pictures. So again, the left side is real, the right side is complex. You don't see much difference between them apart from the fact that, of course, the real part has this symmetry over the real axis. But what I'm asking for is that this eigenvalue or this eigenvalue. I'm asking for what is the rightmost eigenvalue, because this is the eigenvalue which determines for me the blow up of this Roberts-May equation. And the theorem is the following, which is a very recent theorem by Giorgio Cipollone and Yuan Xu. Is the following, that sigmas are the eigenvalues of a complex IID matrix. So again, IID means that the matrix has completely independent zero expectation, 1 over n variance, random variables in the entries, but apart from that we don't assume anything else about distribution. You take the maximal real part, so this is the rightmost, the real part of the rightmost eigenvalue, and then it's like what I started with the Gumbel distribution. So this is supposed to have a typical size, which is given by this formula. It's given by 1, which is the radius of the circular law, plus something else, which is an explicit formula depending on n. By the way, here you also see these 3-term asymptotics, the log n, log n, and the constant term asymptotics. What showed up at the very beginning when I presented the Gumbel distribution for the extremal of a Gaussian random variable. The structure is similar. So you subtract the right object and you rescale it by the right object again, according to the usual spirit of any limiting theorem, and then it converges to a Gumbel distribution. So that's the main theorem, that the rightmost eigenvalue is Gumbel distributed after appropriate rescaling. And this was an old conjecture for Shafai and Charbord. We also have an analogous result for the spectral radius. The result looks exactly the same, just the gamma m is different. And of course, the main intuition behind that is that, maybe let me come to the picture back. So the main intuition that the largest eigenvalue of real part, these are eigenvalues which are the possible candidates are few eigenvalues in a certain rectangle. Maybe I can show it here. Better, there's an appropriately scaled rectangle which contains finitely many eigenvalues. These contain sort of the contenders for the largest maximal real part. And these eigenvalues are sufficiently far away that they are supposed to be, or they feel to be roughly independent. Of course, proving that it's a different story. Typical eigenvalues are not literally speaking independent, but far away eigenvalues have a tendency to become independent. So at least this makes it plausible that the result is a Gumbel distribution, which is essentially a maximum of independent random variables. Actually, our proof follows a very different path. It's a very good intuition. It's a nice intuition of thinking the eigenvalues, the extreme eigenvalues, to be roughly independent, but the proof doesn't work like that. Nevertheless, we do prove a Poisson statistics, so that's my last theorem here. So this just shows that, it just says that you take these eigenvalues, you rescale them in the way that appropriately, so that these are now maybe the picture is easier. So there is a natural rectangle in which these few contenders sit, and then there is scaling, what will be in the formula, they correspond to appropriately scale this rectangle into an order 1 rectangle. So these are the x and the y variables. The precise formula is not important. The important thing is that you get a Poisson distribution. Poisson distribution here is expressed as usual in terms of the Laplace transform of the linear statistics, and then the formula, this formula for any probabilist would tell you that this is a Poisson distributed random variable. Okay. So I think I don't have much time to say anything about the proof ideas, so maybe let me just skip there a few lines, but I don't have much time. Maybe the only thing that I wanted, maybe I just emphasize this thing here, that which goes back to the zigzag strategy, that we do non-Hermitian story. As I said, for non-Hermitian matrices, the resolvent is not that useful, but fortunately there is a formula, it's called the Girkos formula, which probably known also to this community in one way or another. It relates the non-Hermitian eigenvalues sigmas to certain Hermitian eigenvalues in the following way. If X is a non-Hermitian matrix, in our case a random matrix, but the formula is true for any matrix, X is a non-Hermitian matrix with eigenvalues sigmas, then you can form the so-called Hermitization of this X, which is a twice as big block matrix, and then it has an extra spectral parameter Z, so X minus Z and X minus Z conjugate in the two off-diagonal blocks, which by construction is a Hermitian matrix. I like Hermitian matrices because for Hermitian matrices the resolvent is a good object. And the formula is this one, this is Girkos formula. It tells you that if you take a linear statistics of the non-Hermitian eigenvalues, which is the sum of f is any test function of the non-Hermitian eigenvalues, then it can be expressed by a double integral. The double integral on one hand contains the Laplacian of this test function f with an additional spectral parameter z, and this is a spectral parameter that you have to put in the Hermitization, and then you have to compute the resolvent of this Hermitization and integrate from along the imaginary axis. And it's a beautiful formula. If you haven't seen them, then I recommend to try to prove it. It has an easy proof, and surprisingly nice formula, which is especially essential for us because it relates something which is non-Hermitian, which is hard to compute, to something which is Hermitian, which at least is more tractable. So this is what we do. This is the basic step, and then we have to study this Hermitian matrix. It's not a Wigner matrix because it's a block structure, but many of our theory goes with some modifications through to that. And the most important thing is that it's an additional spectral parameter Z, which comes from the Girkos formula. And now we have to understand this how the resolvent, which now depends on its own spectral parameter plus this additional spectral parameter, how these resolvents what is their joint distribution. So each resolvent itself becomes deterministic, but if you want to compute correlation functions of say, second moments of this linear statistics in a Gierkos formula, then you have to understand, for example, not just one G, but two Gs together, so one of them at Z1 and another one at Z2. And then in this situation, these are of course these two resolvents are strongly dependent, and then we have to understand their joint distribution, and there are formulas which tell you there is still a law of large numbers behind that, but the way how they look like, so what this product of two resolvents where it converges to, it's much more complicated. Okay, so and then we have a novel method to do that, but I don't have time to do that, so let me just come to the summary. So the main result that I presented to you many overview things, but the new result that I emphasized is that we proved the Gumbel universality for the max real part and the spectral radius for any IID random matrices. And the main technical ingredients is, I didn't have time for that, but what I explained at the last minute is that we extend this what we call the local law to a multi-resolvent situation for the Hermitized resolvent, and we have two new methods to do that, but I don't have time to explain that, so thanks for the attention.
Great. Thank you, Laszlo, for the talk. And we're a little behind schedule, so perhaps it's best if we postpone questions until the coffee break.